All right, so this is the third video in this sequence. If you have not watched the first two videos, you might want to do that. I will link the first two videos in the description for this video. All right, so it's not always possible to determine an antiderivative if you don't have an elementary function. Then if you don't have, then you don't have an antiderivative, and it's not possible to get an exact value for any definite integral that you want to calculate. In particular, it's not possible to get an exact value for an improper integral that contains a non-elementary function. But it still may be important to know whether or not that integral converges. All right, does it have a finite value? So that's what we're going to look at today. So if we take a look at the picture that I've got up here, all right, I've got two functions f and g. The basic idea here is we're going to compare f and g. All right, if you take a look, g is always less than f. So if f converges, then I know g has to converge. If g diverges, then I know f diverges. And that is the comparison test. All right, so the comparison test all right, so we have f and g are continuous functions. All right, and let's suppose that f is greater than or equal to g, and that they're both greater than or equal to 0. All right, for all x greater than or equal to a. All right, so that describes the picture that we have. All right, now, the first part of this says if the antiderivative from a to infinity, g of x, I'm sorry, f first, right, because f of x dx converges, then the antiderivative from a to infinity of g of x dx converges. And then if the antiderivative from a to infinity of g of x dx diverges, then the antiderivative from a to infinity of f of x dx diverges. All right, it's really easiest to see with the picture. If g is always less than a convergent, if g is always less than f, if the area under f is finite and g is contained within that area, then the area under g is finite. And conversely, if g diverges, that is, if the area under g is not finite and f is always greater than g, then the area under the f can't be finite either. All right, the comparison test requires you to find a function to compare what you're given to. So this can be a little tricky. My advice when dealing with the comparison test is always look at the graphs. All right, by looking at the graphs, you can kind of intuit a function that you want to use to compare to. All right, so let's look at an example. We've talked about a particular non-elementary function in previous videos. So let's take a look at 0 to infinity e to the negative x squared dx. All right, and what I want to know is this convergent? All right, now we're not going to know if it is convergent, we're not going to know what it is. All right, because it's not an elementary function, so that means I can't find an antiderivative. So at least at this point, there's no way for me to figure this out. However, what I want to do is take a look at, give me just 1 second here. I want to take a look at my function. So let's move over to the graph and notice. All right, so this is the whole function. We're only interested in 0, 2, right? So I don't care about the rest of that, and I can zoom in a little bit on this. All right, so looking at the graph, I can make some suppositions here. All right, one of which is it looks like it's hitting 0 pretty fast. Okay. So I can expect that it may be convergent. So if I suspect that it may be convergent, what I'd like to do is find a function that is greater than this that converges. All right, so I can play around with some functions, or I can just turn this one on. Okay. All right, so I don't know if we did this one in the earlier video. I'll do it again just in case if I didn't do it in the earlier video. But take a look at e to the negative x. All right, if x is greater than 1, e to the negative x is greater than e to the negative x squared. So if I split this up, right, if I split this integral up and I write it this way, from 0 to 1, e to the negative x squared dx, plus 1 to infinity, e to the negative x squared dx. Well, this is finite. All right, we can tell that from the picture, that that's finite. All right, so what I'm interested in now is the antiderivative from 1 to infinity of e to the negative x dx. If that is also finite, then I know that the whole thing converges. If it's not finite, then the whole thing diverges. So everything hinges on that. Okay. So now that I've got that, let's do this. Let's make myself a little more room here. All right, so I can see on the graph, or at least the part of the graph that I can see. Let's go back and look at that for a second. All right. I can see on the graph that it looks like e to the negative x is greater than this. Okay. I don't want to assume that that's necessarily true further out. So I want to be able to show algebraically that e to the negative x is always greater than my original function when x is greater than 1. All right. So what I can start with is, let's start with what I'm starting with, right? X is greater than or equal to 1. All right. If x is greater than or equal to 1, that means x is not 0. So I can multiply both sides of this by x, which means x squared is going to be greater than or equal to x. All right, so if I negate both sides, all right, then negative x squared is going to be less than or equal to negative x. And then I could take e on both sides, So e to the negative x squared is less than or equal to e to the negative x. And this is going to be true for all x greater than or equal to 1, because that's what we started with. All right, so now I just have to show that the antiderivative of e to the negative x is convergent. And that's actually pretty easy. All right, so I'll move up here. So the antiderivative from 1 to infinity of e to the negative x dx. All right, so this is a type 1. So this is going to be the limit as t goes to infinity. The antiderivative from 1 to t, e to the negative x dx. E to the negative x is an elementary function, and its antiderivative is negative e to the negative x. So I'm going to have the limit as t goes to infinity of negative e to the negative x evaluated from 1 to t. So this now becomes the limit as t goes to infinity of negative e to the negative t minus negative e to the negative 1. All right, so I guess I can go one more step and clean this up. The limit as t goes to infinity. Okay, so that's going to be e to the negative 1 minus e to the negative t. All right, e to the negative t is 1 over e to the t. If t goes to infinity, e to the t goes to infinity. So 1 over that is going to go to 0. So this whole thing goes to e to the negative 1. All right, so we've shown that the antiderivative from negative 1 to infinity of e to the negative t converges. E to the negative x squared is strictly less than e to the negative x. Therefore, that also must converge. All right, so let's write this up. All right, so let's see, where do I want to go here? I guess I'll go down here. All right, so the antiderivative from 1 to infinity of e to the negative x dx converges. And e to the negative x squared is less than or equal to e to the negative x for all x greater than or equal to 1. Therefore, the antiderivative from 1 to infinity of e to the negative x squared dx also converges. All right, so now we can go back to the original problem. All right, we've shown that the second part of this antiderivative here also converges. That means it's finite. All right, so this means that the antiderivative from 0 to infinity of e to the negative x squared dx converges. All right, now we still don't know what it is, right? I still don't know what that antiderivative is, but I do know it exists, right? And that's sometimes just as important to know as knowing the actual value of the antiderivative. All right, I had another example here that I wanted to do, and it is this one. All right, let's do one more example. Let's do the antiderivative from 0 to infinity of x over x to the third plus 1 dx. Okay. So, just like with all my problems, I want to look at what the graph of this looks like. And so I'm going to switch over to the graph here. All right. Nope, that's x squared. X to the third. That's the one I want. Right. Okay. All right, that's the one I want. All right. So again, the part that I'm interested in is this part, right? From 0. Okay. From 0 forward. Now again, it looks like it's approaching 0 pretty quickly. And in fact, if I zoomed out just a little bit more, you would see that it is approaching 0 pretty quickly. So again, I can suppose that this, I'm gonna say that this probably converges. And if that's the case, then I want to find a convergent function that is always greater than it. So let's take a look at 1 over x squared. All right, if I put 1 over x squared in here, all right, 1 over x squared is indeed always greater than, does look like, or I should say it looks like it's greater than my original function. All right, I would actually have to zoom in, but they converge towards each other very quickly. All right, so this looks like something that will work. In order to prove that it works, I have to again come up with I was going to say something. Oh, I have to come up with an algebraic proof. Sorry, brain went to sleep for a second. I have to come up with an algebraic proof that this is true. All right, for all x. So let's go back to the board. All right. Let's go back to the board here and see what we can do. I need x to be greater than 0. All right, so I need x to be greater than 0. 1 over x squared is not defined at 0. All right, but it's definitely greater than the function at 0. So I can just stick with greater than. All right, now it's hard to work with that because all I can do is add or subtract. Otherwise, I get 0 on that side. So I can't proceed with this one quite the same way that I did the other one. But I can start with a statement that is definitively true. And that is that x to the third plus 1 is greater than x to the third. Okay. And in fact, I think I want to swap that around the other way. X to the third is less than x to the third plus 1. That'll make it easy. That'll make it easier as I go forward. All right, so it's fine to start with something that is without a doubt true. Okay. Now, because x is greater than 0, x to the third is greater than 0, which means x to the third plus 1 is greater than 0. All of this says I can divide by it. So I can divide both sides by x to the third plus 1. So on the left, I get x to the third over x to the third plus 1 is less than 1. Now I want 1 over x squared there. X is greater than 0, so I could just divide both sides by x squared. Right? Or multiply by 1 over x squared. So I multiply on this side by 1 over x squared, and I multiply on this side by 1 over x squared. Again, not only is it not 0, but it's positive. So that doesn't affect the inequality. So on this side, I get x over x to the third plus 1, and on this side, I get 1 over x squared. All right, so I have shown, and this is true, again, for all x greater than 0. Now, we've already seen that 1 over x squared converges. The antiderivative of 1 over x squared converges. The p-test says it converges because the exponent 2 is greater than 1. Right? So I don't really have to do much else here. Right? All right, except I do want to pull off. Oh, no, I don't need to do that. Okay. All right, so, yeah, you know what? I do need to pull some of this off here. Take a look. Let me go back to the graph for a second. Let me go back to the graph. All right, take a look. I want to make a statement about the antiderivative of this blue function here converging, but the blue function has an asymptote at 0. So let's pick a point. Let's just pick like 1, right? Let's pick 1, and let's split this off. All right, so I am going to split this up into 0 to 1. Plus 1 to infinity. And the reason I'm doing that is because I know from what we did in the first video that the antiderivative from 1 to infinity of 1 over x squared dx converges. Without a doubt, it converges. All right, again, just like with the last problem, this is finite because it is a finite interval, 0 to 1. You can see on the oh, I'm not showing you the board, am I? Okay, so I'm going to split this up this way, and then this first one is finite. Okay, so I just have to now prove that the antiderivative from 1 to infinity is what I want it to be. All right, so I've already got the inequality here, so that's really all I needed to do. All right, we know by the p-test that the antiderivative from 1 to infinity of 1 over x squared dx converges. We even know what it converges to, but I don't care. It converges. That's all I'm interested in here. Okay, so let's write this up. All right, let's see. The antiderivative from 1 to infinity of 1 over x squared dx converges by the p-test and x over x cubed plus 1 is less than 1 over x squared for all x greater than 0. All right, therefore, for all x greater than 1. Therefore, the antiderivative from 1 to infinity of x over x to the third plus 1 dx converges. So our entire integral, because 0 to 1 is finite, converges. All right, so we have a way to determine whether or not an antiderivative converges by comparing it to another function that it is either always less than or always greater than. Now, I did this whole thing for type 1 improper integrals. It also applies to type 2 improper integrals. All right, so even though this is just type 1, I don't want to go through the type 2 ones also, but you would use the same idea. You just find a function to compare it to, and then Like I said, if your original function is less than a convergent function, it converges. If it's greater than a divergent function, then it diverges. All right, and that would be the end of that.